Hello, guys, welcome to the Techogenius Academy. Today, we are here to discuss the next part of our Linux device driver series. So, today we will discuss how we can handle interrupts in our Linux device drivers. So the introduction to that interrupts are like whenever the interrupt is occurred, so that is just produce an electronic signal from the hardware devices and directed into the input pins on an interrupt controller. So what does that mean? So whenever we are receiving an interrupt, the interrupt controller sends a signal to the processor. The processor then detects this signal and interrupts its current execution to handle the interrupt. The processor can then notify the operating system that an interrupt has occurred, and the operating system can handle the interrupt accordingly. So whenever that interrupt occurs, so there will be some handler to handle the interrupt. So what are they? So the interrupt handler is nothing but it's a service routine. It's just a function that the kernel runs in response to a specific interrupt. Each device that generates interrupts has an associated interrupt handler. Because an interrupt can occur anytime, an interrupt handler can be executed at any time. So it is imperative that the handler runs quickly to resume execution of the interrupted code as soon as possible. The kernel accomplish useful work using a combination of processes context and the interrupt context. So you can think like there'll be a difference between a process context and interrupt context. So why they are different? So why interrupt context is separated? So the kernel code that service system calls issued by the user application runs on the behalf of corresponding application processes that as and is set to the execute in a process context. Okay, so in interrupt handler on the other hand run asynchronously in interrupt context process context and are not tied to any interrupt context and vice versa. So that means like whenever you are serving any system call which is issued by the application side and on behalf of that whatever the processes you are running on the application, so that will execute in the process context. So when interrupt context will come into the picture, so whenever you are dealing with the interrupt handler, okay, because interrupts can occur anytime, so you can't and that will not go to take any other cpu and all these things. So that's why like we are dealing with a different context. So kernel code running in a process context is preemptible, means it can go to some other process to run, but an interrupt context however always runs to completion and is not a preemptible. Because of this there are restrictions on what can be done from the interrupt context, and code executing from interrupt context can do this following: it will go to sleep or relinquish the processor, acquire mutex, perform time consuming tasks, access user space virtual memory. An interrupt handler should be executed very quickly, but if I want to do a more work upon receiving interrupt, then problem will occur that it will miss the interrupt, or at the same time like it will not allow the interrupt to run because the it will take more time to service the work and all these things. So for that there'll be a solution. So the processing of that interrupt is divided into two parts. So one will be your top half and other will be your bottom halves. So what are they actually? So the top half are nothing but a interrupt handler only. So it's just like when your work is time critical, or like it's just like you want to tell that it's a receipt of the interrupt, or you just want to reset the hardware, and that time you can use interrupt handler, or we can say as a top half. And a bottom half is like if you want to do more work, then a bottom half will come into picture, so which is used to process the data, letting the top half to deal with the new incoming interrupts. So interrupts are enabled when a bottom half runs. Interrupt can be disabled if necessary, but generally this should be avoided as this goes against the basic purpose of having a bottom half. So processing data while listening to a new interrupt, the bottom half runs in the future at a more convenient time with all the interrupts enabled. So there are four bottom halves mechanisms that are available in Linux. First is work queue, then threaded IRQs, then soft IRQs, and last is taskless. So the summary of this interrupt handler is like whatever the points you have to remember, that interrupt handler cannot enter into the sleep. So to avoid calls to some function which has sleep, okay, and whenever the interrupt handler has part of the code to enter the critical sections, use spin locks. So why we are using spin locks when we are dealing with the interrupts? Why? Because spin lock will check they are like whenever the interrupt is free, that from the interrupt contest, and it will acquire the lock, okay, rather than the mutex means like if that lock is available, it's okay, otherwise it will go to sleep, okay. So because if it it's just like if it couldn't take mutex, it will go to sleep and until it takes the mute, okay. So that's why we are using spin locks, okay. So we will use spin locks in the next part of our Linux device driver. So I'll explain you each and everything in a coding. So next is interrupt handlers cannot exchange data with the user space. Interrupt handler cannot be called repeatedly. When a handler is already executing, its corresponding IRQ must be disabled until the handler is done. Okay, interrupt handler can be interrupted by high authority handler. If you just want to avoid being interrupted by a high qualified handler, you can just mark that interrupt handler as a fast handler. Okay, and however, if too many are marked as a fast handler, the performance of this will degrade and the interrupt latency will be longer. So, what is interrupt latency? You have to check. Okay, that is a question for you. Okay. Okay. So now what are the functions in interrupt handling? um, First is the request IRQ. In that, the arguments which we are passing first will be a IRQ. IRQ is nothing but this interrupt number, just a IRQ number to allocate. Other will be your handler function. Third will be your flag. Flag can be either zero or a bit mass of one or more of the flags defined in the Linux interrupt .h header file. So the most important of these flags are IRQF disabled, shared, and timer. So we will use the shares. Okay. So shared means like that interrupt where like interrupt will occur on the interrupt line, and that will be shared among all that interrupt lines. Okay. So next will be your name, used to identify the device name using that IRQ, and you can see your interrupts in a cat proc interrupts. So we will just see the list of that whatever the IRQ number is assigned to that device name, and last will be your ID. So that is like just shared by many devices. When an interrupt handler is free, they have provided a unique cookie to enable the removal of only the desired interrupt handler from the interrupt line. Without this parameter, it would be impossible for the kernel to know which handler to remove on a given interrupt line. So you can pass null here if the line is not shared, but you must pass a unique cookie if your interrupt line is shared. So this pointer is also passed into the interrupt handler on each invocation. A common practice is just to pass the device driver structure. This pointer is unique and might be useful to have within the handlers. Okay, and but to free the interrupt handler, we have the free underscore IRQ, and first argument is the IRQ, which is the IRQ number, and the other will be your ID. Okay. So I have just written a code So so this is the code which we are working on. uh, So what I have done, this is the init module where we are creating a CDAS structure. We are adding the device into that. We are creating the class, and this part is we are requesting the interrupt handler. Okay, so request underscore IRQ number. So there'll be a different IRQ numbers of that particular interrupt. So suppose for timer 0, for keyboard it's 1. So for mouse, for different devices there'll be a different numbers. So in this tutorial I will show you, like, whenever I will press some key on the keyboard, so that interrupt will occur, and we can see that logs in the D message. And second will be your IRQ handler, which is nothing but your function. And IRQF shared is like your interrupt is shared among the different interrupt line. And this will be your corrector device, which we can see in the list when we will do this cat proc interrupts. And last will be your structure. Okay. Later on, if this is not properly registered, so we can just display that your IRQ is not registered properly, and we can just go to uh, this call free IRQ, and we'll just free the interrupt. Okay. If it's successfully done, then what it'll do, it'll just go to your handler function. Okay, so what I have done, I have just defined the macro here, IOQ number 1. Okay. And I'm whenever the interrupt occurs, it will go to this interrupt handler and it will increment the I value. I'm just printing that I value, and after that and I'm returning the IRQ handle flag. Okay, so we will do, we will just run a make command. Okay, so we will insert the module. Yeah, great. So then we can see in the list our interrupt is registered. Okay, corrector device. Great. So I'm just see, like, after inserting the modules, I have pressed many keys like cat proc interrupts, and now we are just checking the logs here. So maybe, like, we can see the interrupt handler, and we can. Okay, so as you can see, interrupt is occurred, and it's incrementing. Okay, so again I'm pressing D message, so just see that. Okay, uh, the, the number is increased. Okay, so we can remove the module like this, D message. Okay, so to just delete the logs from the dmessage, we can use dmessage -c. Okay, okay, there are no logs. Okay, thank you. And make clean. So now our next session is like how we can handle bottom halves, how we can handle tasklets, work queues, soft IQs, thread IQs. So that we will discuss in the next session. So if you like this video, please don't forget to like, share, and subscribe. Thank you so much.